Hey there, thanks so much for having me. I've got a lot of slides, so we're just going to get right to it. So AIQC stands for Artificial Intelligence Quality Control. So people are pretty crazy about QC in all respects in bioinformatics, except kind of when it seems to come to AI. It's kind of black box and a little magical. So it's at its core, AIQC is actually an experiment tracker. So if you want the slides, I'm going to be going through them pretty quickly. So there's a link to them. I'll put this up at the end as well, so you don't have to be taking pictures and stuff. So we'll talk about an overview of the framework, and then we'll talk about why I built it, some of the origins, the pain points that it aims to address, and then we'll move on to what the framework actually is and how it solves those challenges. Then we'll apply it to some gene-based expression analysis and design some virtual drugs, talk about the big picture of kind of what's next. So like I mentioned, at its core, AIQC is an experiment tracker. When I looked at the existing tools in the space, I didn't like their APIs. I wanted something that was pure Python, not like command line YAML. And as I started to build this, I added support for TensorFlow and PyTorch, and you could tune models purely in Python. And the real value was when it came time to evaluate the models. So I automated that. For every split and or fold that you're using, it will provide you both metrics and charts, and you can compare them in the user interface or use the API to interact with them. However, I realized that in doing so, it was almost impossible to do this unless you were taking responsibility for how the data is prepared, how it's stratified, how it's pre-processed. And then if you're doing that, then you might as well handle the post-processing and inference as well. And then you can really start to generate insight. So AIQC handles all of that. And there's zero setup. It's just a pip install. When you import it, that's actually going to trigger the creation of a SQLite database that keeps track of all of this. So everything is reproducible. And then there's a Dashplotly user interface that's included in the Python package. And you can just pull that up with another one-liner. So it's pretty simple to get started with. And in doing so, I've provided a declarative API for basically protocols for different types of deep learning analysis for all the standard types of analysis and data types that you would want to conduct. And we'll go through what that looks like. Here's a bit of eye candy. This is the experiment tracking user interface, right? So when you run a queue of models, it'll plot all of the splits or folds and any inference you've conducted on one chart. So you can see which model is the most generalizable, which model is the most performant. You can change up top the type of score that you're looking at and set thresholds. All the hyperparameters are right there. When you find the best model, you slap a star on it. And then if you want to compare two models head to head, again, all the metrics and charts are automatically created and at your disposal, at your fingertips. So you can just kind of scroll up and down through them to get a really in-depth comparison to make sure you're finding the best model. And here's what I added for the purpose of, well, this conference. It's a UI for inference, and it handles all the pre-processing and post-processing for you. So on the left, you have the features rank ordered by feature importance, and you can tweak them to make new predictions and virtual samples that don't really exist in nature. The last overview slide is that what this really is like an API that unifies the PyData NumFocus ecosystem with the deep learning ecosystem, because there's a huge gap there. So up top, you've got the actual machine learning frameworks. Down bottom, all the raw data. On the right is kind of how you interface with it in Jupyter. Love those guys. And on the left is the visualization. I don't know if left and right is the same in the crowd, but me, I'm self-taught. I've got like 3 years of business college education, but I've had successful startup exits. I found the genomic space, and I help, as my trade is a product strategist for analytics platforms, and I wrote every line of code in AIQC. We'll talk about Whooshi Nextcode and what that is next. So my experience in cohort analysis really begins in Iceland. So Decode was first in population genetics. Out of that spun a Nextcode, which was made to commercialize the genomically ordered relational database made by Håkon Gudbrandsson, the Gore father. And Whooshi is collaboration with Wuxi AppTech. So you put that together, you get Wuxi Next code. So it's really designed to handle genomic data at scale, but it all kind of fell apart due to Chinese relations with the West. Anyways, we started commercializing that with that technology with Big Pharma, and we were analyzing cohorts like UK Biobank. We acquired Genomics Medicine Ireland, which has really specific diseases. So I was kind of running my own GWAS there and figuring out what's the next fine mapping algorithm that we're going to implement at scale and distribute that in Kubernetes and Nextflow and all that jazz, right? And now I'm actually at the point where I just got approved for TCGA access for AIQC. And we're going to run a cross-sectional kidney and bladder cancer study with Dana-Farber and Alabama to see what comes out. But I have actually done some work recently with Harvard Med looking at the proteomics of Alzheimer's. So they aggregated samples of the tau protein, which acts like a cast for neurons, and it kind of degrades over time. And the question was, can we train a predictive model and then permute that to figure out which post-translational protein modification sites are driving the progression of the disease? And as you can see here, we did get a highly accurate model. And these are the protein, I guess we call them accession IDs in UniProt, of what's driving the disease. So if you look at this feature importance, it's not like what everyone else is using, SHAP. I tried to use that and it wasn't up to date with TensorFlow. Maybe it didn't support PyTorch or didn't support convolutional or recurrent models. So I just kind of wrote my own, and it's pretty good, not great at categorical. When you permute a categorical feature, you're really kind of limited to the distribution. Anyways, I got a lot of slides. We're gonna keep flipping through. But yeah, those are the sites that are driving the progression of Alzheimer's. Pain points in deep learning. So association studies date back to the Victorian age, right? And they're not necessarily that flexible, right? They can't handle feel free to correct me if I'm wrong in a question, but they can't handle imaging data or time series data. You can't do a multi-label study where you're looking at disease subtypes or disease progressions. As they said in the first keynote of this week, how many hypotheses are we actually testing when we're running an association study or a FEWAS, right? And one of the nice things about deep learning is that, or machine learning, you get an algorithm at the end. And although polygenic risk scores are possible, that's not really what GWAS is designed to do. It's hard to parallelize. It's a lot of these algorithms, the nth fine mapping algorithm, it's written by a grad student. It's not designed to burst out to a massively scalable cluster, whereas TensorFlow definitely is. It abuses your cores. It'll consume your machine. You don't even need to scale horizontally. So neural networks, I love them. They're really flexible because you can jam in information. And what you're really trying to do is do a transformation to a future state. Well, not future, but another state of information. That can be in a conclusion, like a regression. It can be a categorical classification. It can be more information. These are Turing Award-winning algorithms, and they solve themselves. You don't have to tweak your own parameters in a differential equation. And it's great to have this tool because we don't have to rely on the nth fine mapping tool to come out. So deep learning allows us to answer deeper questions. You can use multimodal data. You can forecast the future. You can do multi-label analysis. However, the problem is whenever you change the type of data that you're working with, tabular, image, sequence, the entire workflow has to be essentially rewritten from scratch. And there's a lot of glue code that has to be written in machine learning today. And every member is kind of patching together their own glue code. And there's a lot of pitfalls along the way if you're not a data scientist expert. And pretty much the whole top half of these problems can be solved by, I love the PDF version of what emojis look like. Came out a little silly, but the top half can basically be solved by introducing the use of validation splits that are encoded by fit on train only. And the bottom half can be solved by kind of keeping track of things in a systematic approach. But when you start to do these things, you end up juggling a lot. You've got multiple splits, you've got multiple encoders, different encoders for different columns. I got a grant from the Python Software Foundation to help solve the sliding time series windows. So if you want to do stuff like fold count in a cross-validation, you just say fold count 5. If you want to do sliding time series windows, you do window count equals 5, and it'll just kind of solve it for you. So there's a lot of things to juggle. I'm not going to talk about all of them, especially during inference when you want to be able to pre-process and post-process 6 months down the line. And if you want your team, your lab, your small biotech startup to be able to do this, it's really tough because you need 3 different sets of skills. And that's expensive. It's hard to maintain that person from, the FANG companies. And it's almost infeasible to go and learn it all on your own. You kind of have to drop out of society. So solution, the framework itself, I basically created building blocks for machine learning. So you don't have to do X-train, Y-test scripting. And this is the low-level API. And you kind of stack these up to create experiments. And then I realized that in the different workflows, I was essentially doing the same thing every time. So I came up with a declarative API that allows you to, it'll stack those building blocks behind the scenes for you. You just describe the state of the analysis that you want to conduct, and it'll do it for you. Here's like an overview of what that looks like. You have a pipeline that allows you to ingest and stratify data as well as pre-process it. And the post-processing is like the reverse engineering of that, which happens during inference. And then it takes a similar approach to, I guess, PyTorch Lightning, in that you define components of your model, like function to train, function to build, function to optimize. And a lot of those are actually dictated by the type of analysis that you're conducting. We'll see what that looks like. So here are the 3 classes of the high-level API. You have that pipeline that is going to feed into an experiment. The pipeline data gets cached. Each experiment job will pull from that cached data. And then eventually, when you want to run inference, it'll go back and look at what the original pipeline was for that trained model and use that for you. So within pipeline, you see this input object. That's the first one, right? So if you jump into the subclasses of the high-level API, here's what that looks like. It's declarative. So a data set can be tabular, sequence, or image, and it comes from all the different types of objects that you would expect in data science. And there's a lot of different ways to pre-process. You don't have to use any of them. They're all optional. But when you do go to encode your data, it's extremely easy. Here, I'm targeting a specific D type. And I'm going to apply, I'm going to scale all of those using scikit-learn encoders. And then the remaining, what's left over is, the city column. So I'm going to target that by name and one-hot encode that. That's all I have to do. And it handles the decoding for you. Preserves the fits. And this, it looks hard, but it's not. Like if you go onto the AIQC, docs.aiqc.io, there's examples of how to do all this stuff in TensorFlow and PyTorch in Jupyter notebooks. And you'll pick up on it pretty quickly. How does this compare to everything else out there? Well, it's really easy to set up. All you have to do is import the package. Everything else is declarative as opposed to manually scripting. And, if you look at all the other user interfaces, sure, yeah, it's possible to do that stuff, but they're basically just showing you the fruits of your labor. But yeah, for vertical scale, we'll talk about partnerships with cloud platforms that I'd like to develop. Now let's actually apply it. So first, we're going to look at some pretty clean data that got leaked out from TCGA. It's on the UCI, which is like the go-to place for machine learning data sets. We will have a matrix of 20,000 genes. And they're going to be coming, we're going to try to classify the type of tumor and then rank the genes that are driving those tumors. So to start, we take that expression matrix, we say dataset tabular, then we have a pipeline, and for features, we're going to use that data set that we just ingested. We're going to get rid of the sample ID column just because that's not going to be informative. And because they're all floats, we're just going to encode them using standard scalar. Moving on to our label. We're going to use the label column here, which will automatically get excluded. Class is the type of tumor. And we're going to one-hot encode those because this is a multi-label classification problem. And then when we go to stratify our data, we just describe the sizes that we want. Okay, so for experiment, this might look, it's a neural network. It's not really that complex. There's only one layer in it. And I might automate this in the future with McDonald's hamburger size, small, medium, large, based on, because it knows what your features are. It encoded them itself. So I could do that in the future with the UI. But you'll notice that different things are passed in here. So it knows the shape of your features. It knows the shape of your labels. So you can just drag and drop those into your model. And then hyperparameters are passed in as keyword arguments into every component function. Then we assemble an architecture that consists of those component functions. There's a lot of defaults like optimize and loss or default based on the type of analysis that you're conducting. It also supports PyTorch, and I wrote basically Keras for PyTorch. So it's easy to use, but I don't recommend PyTorch. And then you can permute as part of you can permute the columns, so shuffle the column and rerun it back through the model to get automated feature importance. You can also do that after the fact. And here's the results. So this pretty much tells me that tumors are a function of expression. Like I've ran this for like 10 epochs just to see if like the model was configured correctly, and it just ate it up. So, and here, I think these are entrees IDs, but they weren't provided with the actual data set. And when you want to fetch this information, it's just, plot confusion matrix, plot feature importance. You don't have to like do any data wrangling. Okay, so, and it's almost boring to look at image and other types of data because all you're doing is providing a different data set type. The rest is all the same. It's just declarative. Okay, now we're going to look at some dirty data, which is actually fun. We're going to design some virtual drugs for the MAPK pathway, some kind of kinase. And this is also out there on the UCI repo for data sets. So we've got 60,000 compounds, and we want to know if it's going to be active or inactive in this pathway. And we've got 200 structural characteristics that we're getting from our high throughput screening. Problem is the data set is really imbalanced. Only less than 1% are active. And we're going to try to rank which characteristics are designing it. So it's just a linear model. So we'll jump straight into the interpretation. If I filter by accuracy basically above half, then I am only left with 2 models that succeeded. And I'm going to run with this one on the bottom because it's simpler. It uses less neurons, which means it's probably more generalizable. And if we compare the models head to head, this just kind of shows off the different metrics that are in there. You see I got a smoother loss curve or smoother learning curve on the model with less neurons. There's rock curves in here as well as precision recall curves, and then the confusion matrix, right? And you can see, I think I chose this one because it's better at predicting success than failure. And that's what I care about, especially when only less than 1% are going to be successful. Here's the features that both of those models are learning from. And you can see they're both kind of gravitating towards the number of hydrogen bond donors. And then there's a bunch of secondary features. Right, and this is what we wanted to get to. So this is the simulation user interface. All the features from our model are automatically populated with the median from the data set. If you moused over the column name, it would show you metadata like the actual importance and the distribution of the columns and stuff. But if we run the median through and just get inference, we'll see that it's a failure. However, if we tweak some of these top features, and I'm not a chemist, maybe this isn't even synthesizable. This should honestly be done by a chemist or a reinforcement model with penalties for what's actually synthesizable. We get 95% success in a data set where less than 1% of compounds were successful because we know what features are important to this virtual space. So machine learning models can explore a loss space for minimums, but so can humans. I mean, we just did it right there just by flipping a few switches. All right, so in the big picture, I'd really like to bring deep learning to all aspects of genomics, proteomics, allomics, and I think the best way to do that would be to partner with a cloud platform where they're processing the omics and designing the cohort, and then you kind of jam that into a really flexible neural network to answer the question that you want to. I think these guys are really incentivized to do that because you've got these other players that are starting to creep into the space. If you look at what pharma's doing, they're all starting to look at machine learning as like the 4th pillar of pharmacology, and they're partnering with early stage AI companies. So this presents a hurdle for labs and biotechs that are trying to do research. So, are you going to machine learning train your bioinformaticians and have them writing scripts from scratch? Are you going to go compete for machine learning talent? Are you going to build your own in-house platform? Just use AIQC and let me know if you get stuck. And that's it. Yeah, so there are the slides if you'd want them, and I'm happy to take any questions.
Anyone have any questions? Do we have any questions online?
Let's see. So, yeah, very nice talk and system. I'm curious if you can output some kind of manifest of the metadata or provenance of all the steps that happen.
So that's kind of the notebook itself. So when you end up writing the notebook, you get unless you've essentially got that kind of manifest, because the language is declarative. So if you look at something like Terraform, that's effectively a manifest for how your cloud platform is built. And AIQC, in being declarative, provides you that manifest naturally as you write the code. But it's also preserved in SQLite too, so you can go in and query that yourself.
Okay, so I guess then if you wanted to do some meta-analysis of notebooks, right, you would do it at that level, right? Is that?
When you say meta-analysis, are you saying like comparing across different analyses?
Maybe compare two large experiments, right, that cannot be easily merged into one flow analysis, right? Sequential analysis, yeah.
So that's kind of what this interface is for here. It doesn't allow you to compare raw prediction values, but it'll allow you to compare the models themselves.
Thanks. I think we have one more question up here coming. Thank you.
Really neat talk. Quick question on, is it Slurm aware?
Sorry.
Can you automatically run jobs on a big high performance computing system, submit Slurm jobs automatically?
It runs anywhere Python runs. So the answer to your question is no, but it could easily be configured to do so.